Good morning. I'm sharing the screen here and okay, so let's start. Don't forget exam 3 is the day after tomorrow. First thing you have to know. And let's take a look at the syllabus. Okay, it goes. Yeah. Okay, so the exam 3 is going to be chapters 22, 23, and 24. Okay, let's see. 22. Let's take a look at 22, 23, and then 24. I see. 22, 23, and 24. That's the one. Material for the exam. Okay, there will be only 22, 23 plus labs 5 and 6, right? Which already posted there in your Google Drive, in your group folder in the Google Drive. Unfortunately, we didn't have time to cover polarization, although it's an important topic. Okay, but has a neat polarization has a neat application because it's we use polarization to create 3D movies. Okay, and that's what we have when we are using those special eyeglasses. We have one type of polarized lens on the right eye and another type of polarized lens on the left eye. And you must have the two eyes to see the effect, to have the illusion that the picture is in 3D. Okay, you must if you use just a single eye, you're not gonna see the 3D effect. That's one of the important applications of polarization. But there are others. There are other applications. That's just one, the one that you should be familiar with. Okay, and let's see if there is anything else here in the syllabus. Okay, here you go, refraction of light. Our priority is to finish refraction of light. Let's see if you can get into special relativity. And we're gonna have the exam and then another meeting and then a holiday. And here you go, here's the last class, and then finally 2 days before the final. Okay, and let's take a look at the homework. Here's the homework already posted. Let's put that in the list. Posted the day after. Posted the homework for chapter. Which chapter is this one? Let's take a look. Chapter 25. Reflection and mirrors. Okay. We'll post the homework of the remaining chapters soon. And save it. So let's see where we start in the refraction. Yeah, we stopped the. Let's see here. What am I doing here? Okay, that's the lab 8. Let me emphasize here. Here you go. Lab 8. So we stopped it in refractive index. We did see, why is it doing that? Shouldn't be like that. Okay, now we got it. And I'm going to. Oh man, sometimes this guy, he start doing this problem. Oh, see that I cannot highlight it for some reason. So strange. I can highlight it here. Let's see if I can highlight. I can highlight here. I can, but I cannot highlight here for some reason. Must be some sort of bug in the software. Let me. That's why I must have had that. That's why I had. Yeah. See, if I insert the page break, the problem goes away. Okay. Strange, right? If you know the reason for that, let me know. Let's see. I can highlight it here. Let's see, but I cannot highlight here. See that? So strange. We need to have a break on this page. It must be a bug in the software, okay? Bill Gates gotta fix that. If you end up working for him in the future, tell him about this bug. And it's good that we have it documented here. Now the question is how to reproduce it in another document, right? The first time I see this problem in my life, in my entire life. Okay, so here you go. Lab 8 is here, and we covered the so-called Snell's law. Here you go. That's Snell's law. Don't forget that Snell's law is a consequence of, let's summarize here. Snell's law, Snell's law, as well as the reflection law, are a consequence of the least time, of the principle of least time, Okay, not least space. Don't forget, not least space. Least space, right? Very important difference. And I'm gonna put in capitals here. Here you go, not least space. So let me, this one, I'm going to, this one right here, okay? That's one of the first postulates. That's the first postulate of ray optics, or geometrical ray or geometrical optics. I'm gonna get here roster. Good. So I have my roster here now. Okay, so here you go. In this case, that you have an homogeneous medium, same refractive index throughout this space, you know, the principle of least time coincides with the principle of least space whenever the light travels from S to C. Okay, this is the least space, but ends up being the same as the least time as well. Okay, whether it's going from S to C, whether it's going from S to A, whether it's going from S to B. Light travel in straight line. It doesn't travel in zigzag unless, you know, you have a different medium in there. The principle of least time, okay, differs from the principle of least space when we introduce a second medium of a different refractive index or a different optical density, okay? The higher the optical density, the slower the light travels. So if light is traveling from the source S to this point B inside this medium, it's not going to travel in a straight line, which would be the principle of least space. It's going to travel in this line here, this broken line, which minimize the amount of time that takes for the light to go from S to B, okay? And that can be proven mathematically when you use the principle of least time. Same thing happens to A and C, okay? And that's the idea of refraction. That's the idea of refraction. Here we have another medium. Here you go. That's the angle of incidence. The angle of incidence is always measured with respect to the normal of the medium. Here's the interface between this medium in the left, air, and this medium in the right, that can be water or glass. And remember, every time when you do the math, applying the principle of least time, you find that when the light travels from a medium of lower refractive index to a medium of higher refractive index, the light ray approaches the direction, the normal direction. The angle of refraction is going to be less than the angle of incidence. Okay? And you have the opposite. When light travels from a medium of higher refractive index to lower refractive index, the light ray moves away from the normal. Remember that? And this angle is given by Snell's law. This is what, again, what's not covered in the book is the principle of least time, okay? They just go straight into Snell's law and call it a law. Another example of the principle of least time is there in my website. Remember, I mentioned it to you, Science Sensor. I took a very nice picture there in my website. Please guide kits. Okay, here you go. That's the figure that I'm referring to. And it's also this figure too, which is a little bit more complicated, okay? The geometry is a little bit. So here we have the refraction again, the light ray moving towards the normal. That's the normal. This is a wedge format. No, that's a situation that's a little bit more complicated than the other situation here. Okay, light is propagating a straight line, right? But when it reaches this bit of higher refractive index, it refracts towards the normal. Okay? And that's what it is. Sections 26.1, 26.2, and 26.2 in the book. Okay? So I'm going to here just document in my notes. Okay, Snell's law predicts that a light ray propagating from a medium of lower refractive index to another medium of higher refractive index has an angle of refraction lower than the angle of incidence. Okay, let's see. Let's see, instead of have an angle of refraction lower than angle of incidence, let's write in a different way. You know, refracts towards the normal of the medium. Of the medium. Okay, so higher, lower, towards, away from, towards, away from the normal of the medium, of the interface, right? Of the interface of the two media. That's a better way. And that's what those pictures tell you about. And now that leads to some very important, this leads to some very important consequences. Very important consequences. This leads to a very, not some, to a very important consequence. Okay? It's called the total internal reflection. The total internal reflection. So think about that. Let's see if I have here an illustration for you. We have, here you go. We have this one. We have this illustration right in here. You are underwater. You have a laser pen with you, and you shine light at the interface between the water and the air. Okay. So what's going to happen? Some of the light is going to refract. Okay. Can be a glass too. Doesn't have to be glass. It doesn't have to be water. Can be glass as well. I'm going to do like that. Here you go. Some of the light is going to refract, and some of the light is going to reflect. Okay. If the incidence is normal, the angle of incidence ends up being equal to the angle of refraction. Okay. That's a special case of Snell's law. See, refraction, normal to refraction, and reflection. Like that. Okay, energy must be conserved. Okay, power here of the incident light must be equal to the power of the refracted light plus the power of the reflected light. That's a must. But let's continue. Let's increase the angle of incidence here, and let's see what are the consequences. What consequences that we're going to end up having? Angle of incidence increased, and the angle of refraction, must increase as well, right? And we see the angle of refraction from the normal increasing. That's the normal. Normal, or for a curved medium, should be the normal, right? For a flat medium like this one, the normal coincides with the perpendicular of the interface between the two media. Now, there will be, because of this type of behavior, there will be a point in which there will be an angle in which the light is not going to refract. The refraction is going to end up being parallel to the interface. Okay? And the power of the light is going to be completely reflected. That's what we call total internal reflection. Okay? And this angle that you see here, we call it the critical angle. Okay. That's a very important effect that we have. Let's see if I have a better. Yeah, okay. That's a very important effect that you have that's used in fiber optics, which again is my specialty. When the light reaches the critical angle, the angle of refraction ends up becoming 90 degrees, and all the light is reflected. Total internal reflection. Let's write it down. Okay, total internal reflection. If light from a higher refractive index is incident at the interface between a higher and lower refractive index, it is possible to reduce the amount of refraction if you use an angle of incidence. If you use a proper angle of incidence, it's possible to reduce the amount of refraction to zero if you use a proper angle of incidence. This angle of incidence is called the critical angle. Okay? At the critical angle, comma, the angle of refraction becomes 90 degrees. Okay. The angle of refraction is 90 degrees, not becomes, but is 90 degrees. Let's take a look. Let's get Snell's law. So you end up, now you already know how total internal reflection happens, right? Here you go. So let's make the angle of incidence equal to the critical angle. Critical angle. When the angle of incidence is equal to the critical angle, the angle of refraction becomes 90 degrees. And then that's how you find out the critical angle. Okay? Angle of incidence equal to the critical angle. Angle of refraction is equal to 90 degrees. Okay. Sine, oh, what's going on here? Here you go. Sine of 90 degrees, you already know it's 1. And now that's the condition for the critical angle. That's the mathematical condition for the critical angle. And by the way, we observed this in experimentally over and over again. I did this experiment with my students several times, okay? So here you go. Critical angle. At sine. And now you can use this formula to find the critical angle for different index of refraction, for different combinations of the index of refraction. Okay? let's do that with Excel. It depends on the index of refraction here, right? Well, now let's ask, what is the advantage? What is the advantage? What is, before we go into that, right? What is the advantage of using the, oh man, see, misbehaving. What is the advantage of using the critical angle? Okay. There's a very important application, and that's in optical fibers. Okay, when light propagates at critical angle, there is a much smaller amount of loss inside the medium. Okay, and I'm going to, that's the advantage. And let me give you an example right in here. Okay, so here you go. We are looking just at the upper surface, right? What about at the bottom surface? What about at the bottom surface? You know, you have seen something like that in my picture, right? If you illuminate perpendicular, you know, all the light is going to be lost because none of the light is going to propagate along this device, okay? Here, if you illuminate in this direction, you know, some of the light is going to be lost. Some of the light rays is going to be lost, but some of it, you know, survives. However, if you choose an angle of incidence that's equal or greater than the critical angle, this light that is inside this device, this optical device, will propagate for a much larger distance. That's the principle of optical fibers. Optical fibers that I use for telecommunications take advantage of the angle of critical, the critical angle, or the phenomenon of total internal reflection, to send communication signals to thousands and thousands of kilometers, okay? There are underwater cables of fiber optics that transmit telephonic signals using light for thousands of kilometers, hundreds and thousands of kilometers. That's the advantage. Okay, so what you see right in here is what we call a waveguide, a device that guides a wave. This type of phenomenon happens not just with light, but with other types of electromagnetic radiation. We have something like that for radio waves. We have something like that for visible light, for infrared light, for UV light, for X-rays, even X-rays, okay, and gamma rays. You can build what we call waveguides for all this type of electromagnetic radiation. So let's write it down. Okay, when light propagates at critical angle, at angles greater, right, or equal than the critical angle, there is a much smaller amount of loss inside this medium, loss of light inside the medium. Optical fibers take advantage of this phenomenon to propagate light along several kilometers of fiber, if not 100, if not 1,000, several kilometers, if not 1,000. Fiber. That's the principle of total internal reflection. Okay. You can do that with glass. You can do that with water. Now let's do a quick exercise, right? And let's go right in here. We're going to start N1. N1 is going to be refractive index of air or water or air or vacuum. Okay, and I'm going to do that. Oops. Okay, and we're going to do that for different types of media. Okay, and we're going to use the critical angle here. We're going to find out the critical angle, and by the way, the critical angle is given by the arc sine. A sine of what? Going back to the notes. N2 divided by N1. N2 divided by N1. And then I'm going to give some values for N2. Let's start with water. What happened here? A sine. What the heck happened here? Let's see if I did anything wrong. No, there's nothing wrong here. Strange, huh? Oh yeah, must be something. Okay, so let's see. Yeah, there's a mistake in the equation. It's N2 divided by N1, right? I put N2, N1 below. Yeah, I inverted. It's supposed to be N1 divided by N2. Yeah, otherwise you're gonna get N1 divided by N2. Nobody picked up the mistake, huh? N2 divided by N1. Oops, wait a minute. Yeah, it cannot be N2 divided by N1. Let's see, what did I do here? Let's see. Let me pause momentarily. Here you go. Yeah, okay, so don't forget, under this condition, N1 must be greater than N2. Otherwise, you're not going to get total internal reflection, right? So going back here you go. Now, N2 is greater than N1, right? So now we can get this value for the critical angle, which, by the way, is in radians. We want to change that. When I change that to degrees, right? Degrees. And degrees, oops, degrees, convert radians into degrees. We get this angle here, 48 degrees. That's the critical angle. So if you are underwater, like here, this case, the total, you get total internal reflection whenever the angle of incidence is 48 degrees. Okay. Now let's go to another index of refraction, 1.5, for instance, right? Which is the index of refraction of glass. So we get a slightly lower critical angle. And that's exactly what happens when we increase the refractive index of the medium. The higher the refractive index of the second medium, the lower the critical angle, right? Let's take a look at another medium that we have, a medium here that we put in our table. Air, water, right? Most glass is diamond, 2.4. 2.4, 3.41, right? So click and drag. See, in diamond, you require only 24 degrees for the angle of incidence. If you're inside diamond and you have a light source there inside diamond, a laser, easier to do that in water, right? Because water is liquid. You can be underwater, take your waterproof laser underwater and play a little bit with it. Okay? So those are the 3 numerical examples of how you can achieve total internal reflection within a region, a medium of higher refractive index. And that's the 26.3. Okay. You have to go. I'm going to show you what's in the book. Okay. There are 20, the refraction. Okay. Total internal reflection right in here. Here's one example. Salamander with snout near the surface of the water. Some of the light from its body strikes the air-water interface at angles greater than the critical angle and is reflected. Thus, the interface looks like a mirror and forms the image of the upper part of the photograph. Last one. Go diamonds, right? Here go the case of a prism. Okay. We have devices like that. You can reflect light totally without using any metallic surface here, without aluminizing the glass. You can do that provided you have an incidence here that's greater, light incidence here that's greater than the critical angle. So the surface here of your prism totally reflect the light that's incident at an angle of 45 degrees. Here too. Here too. That's one. Another application, you go optical fibers, see total light travels and the total internal reflection here inside the fiber. And because of that, you lose very little light. This is a bronchoscope to examine the lungs of a patient. And bronchoscope uses an optical fiber. You can image objects using optical fibers, okay? So endoscopy, we call it that endoscopy. In the field of medicine, optical fiber cables have had extraordinary impact in the practice of endoscopy. For instance, a device called an endoscope is used to peer inside of the body. Okay, so it's possible to create images with an optical fiber, which, by the way, uses total internal reflection. Now, how to create the image, that's another story. It's more, it requires a rather complicated procedure. And cables, yeah, another application of optical fibers in astroscopy. Okay, with only a tiny incision and minimal damage to the surrounding tissue. Okay, so a doctor, okay, he inserted this optical fiber here in the knee of the patient. My brother went through that procedure, by the way. my younger brother. And optical fiber use total internal reflection. Okay, now I'm going to skip this part here, polarization. And what I'm going to do, I'm going to talk about dispersion. So 0.1, 0.2, 0.3, okay? 26.1, 26.2, 26.3, and we're going to skip 26.4. We're going to go chapter 26, refraction. Okay, sections. Okay, then we have now the phenomenon of dispersion. Phenomenon of dispersion. What's that? What is it? Okay. In dispersion, phenomenon. Oh. In dispersion, let's see how I'm going to write this. State that dispersion is characterized by the fact that light of different wavelengths travel at different speeds. Okay. In other words, each wavelength of light sees the medium with a different index of refraction. Okay, but the difference is minimal. But the difference is but keep that in mind. But the difference is very small. Okay, keep that in mind. Difference is very small. So I'm gonna give an example. If red light has an index, consider, example. Consider, so you can understand better, a piece of glass. Okay? If red light sees an index of refraction of 1.5, okay, comma, blue light will see an index of refraction that is 1.51. The difference is very small, but it happens. We can see that, and because of this effect, we can create instruments that can measure the wavelengths of the light. Okay, that's a very important effect that's used to measure. Okay, this effect is used to measure the wavelengths of light with a spectroscope. Let me illustrate that. Dispersion right in here. Okay, so here you go. White light is actually a combination of all the colors of the spectrum. It's a combination of red, green, and blue. This is a very, and I drew white light here for you to see, okay? If you combine red, green, and blue, that's why we have those RGB LEDs, right? RGB LEDs means red, green, and blue. We can create different colors, all the colors of the spectrum provided if you create the same amount of red, green, and blue, you're going to have white light. If you vary the relative amount of red, green, and blue, you're going to create other types of colors. Okay? Now, here you go. If you go ahead and get white light incident at a medium glass, for instance, we call it a dispersive medium. What does this dispersive medium is going to do? It's going to separate the light into its components. Blue light will see a refractive index that's higher than green light, which will see a refractive index that's higher than red light. I'm exaggerating here, okay, folks? I'm exaggerating here, but that is exactly what happens. That's the phenomenon of dispersion, okay? And because of this effect, we can create devices to measure the wavelengths of the light. A spectroscope, for instance, is a prism, is a glass, is a piece of glass, okay? That light goes through it, here, dispersive medium, and when light reaches the other end of the device, they're refracted differently as well, okay? And you will be able to see that rainbow color. That's how rainbows are created. Rainbows are created because of the dispersive effect of water droplets. Okay? So here, you know, red light is going to refract away, right, to a greater amount because it's further away from the normal. Green light is going to refract a lesser amount because it's closer to the normal, and the blue light is going to refract even a smaller amount because it's even closer to the normal. And now if you put your eye here, you're going to see all those colors of the rainbow. Okay, dispersive effect. Let's take a look here. Let's see if you can find a real picture. Dispersive effect of glass. Let's see. Blender cycles continue. Dispersion. Light dispersion. Let's see. Oh, here you go. Now I got it. But I want to see an actual picture. Okay. Want to see an actual picture. Khan Academy. Let's see.
Check out this ray of light. When it enters a new medium like water, its path will bend, and the larger the index of refraction of the new medium, the more the light will bend from its initial direction that it had in the air. This follows from Snell's law, since if the index of refraction is larger, the angle of the refracted light must be smaller, and in order to have a smaller angle from the normal line, the light ray has to bend more from its initial direction. But here's the interesting thing. When you send in white light composed of all visible wavelengths, the colors will disperse and get separated from each other. We call this separation of light dispersion. So why does dispersion happen? The reason for dispersion is that the index of refraction for water and most other materials are actually a function of the wavelength of the light. For instance, if you ask a physicist or look up the index of refraction of water, most sources would say the index of refraction of water is 1.33. But what those sources or physicists really mean is that the index of refraction is pretty much 1.33 for the entire visible range of wavelengths. However, each visible wavelength has a slightly different index of refraction in water. The index of refraction of red light in water is about 1.33, but the index of refraction of blue light is closer to about 1.34. In fact, for most materials, the smaller the wavelength of the light, the larger the index of refraction, which means smaller wavelength light will bend more than larger wavelength light will in most materials. This is why in water, the violet light would bend the most since it has the smallest wavelength for visible light. Blue light would bend slightly less, green light a little less, yellow light a little less than that, orange light even less, and red light would bend the least. So remember, dispersion and the rainbow patterns that emerge result from the fact that most materials have an index of refraction that's a function of the wavelength of the light. And in most materials, the smaller the wavelength, the more the light will bend.
Okay, so the relation is more, like you said, is most materials follow this rule, okay? Most, not all, but in general, we can state that the index of refraction of a given wavelength, I'm gonna put like, and don't forget, it's a very small effect, but although it's a small effect, it's still observable, rather easy to observe, is inversely proportional to the wavelengths. Okay, inversely proportional to the wavelengths. The wavelengths of light. Okay, and then we have tables out there in the internet showing how is going to be the refractive index of different wavelengths for a specific material. Okay, there are optical glasses out there, okay, that documents the refractive index variation we see in the material. Okay, in general, that is not always, right? For most materials, but not all, the index of refraction is inversely proportional to the wavelengths. Wavelengths, right? Wavelengths. There are optical glasses out there that documents the given material in the given material. Okay, so let's go get it. Let's see if we can find it. I want to find one of those, shot glass, for instance. I remember getting the data sheet of many of their glass. There is a company called Shot Glass. Okay, it's Shot Glass. It's a German company, Shot Specialty Glass. They have a catalog that describe each of their glass. They have hundreds of glasses. They manufacture hundreds of glasses. Okay, it's a very important company. It's just so important that during the Second World War, Schott was based in Germany, right? During the Second World War, the guys didn't want to lose all that knowledge that they have accumulated throughout the years. They knew that Germany is going to be leveled up, right, by the Allied troops. So what they did, the story goes that they decided to transfer most of their knowledge and facilities to Japan, which was allied to the Germans, right? And that's what they did. That's some little piece of information that I thought very interesting. A mentor of mine told me that. Okay, let's see. That's short. Let's see if they have. We use cookies. Yes, I agree. Let's go. Let's see if they have. we're not going to spend too much time here, but I just want to give you an example of how the refractive index change, right? Products and Expertise Solution Magazine. Let's see here. Market, maybe products, special selection 2. It doesn't look like they have it here in their website, unfortunately. But they do have, like I said, they do have their catalog. Yeah. Yeah, short catalog. Let's try it. Let's try short catalog. Short catalog optical glasses. See that? Short catalog of optical glasses. At the time that we didn't have internet, I ordered one of those things. It was back in the 90s, you know, and they sent me this huge binder with all sorts of glasses there. Optical glass, ultra high transmittance, let's say data sheets and downloads for optical glasses. That's what I want. Let's see if they have it. Downloads, conflict rich, let's see, raw data sheet, optical glass collection data sheet. Okay. 5.7 megabytes. Let's see this overview. There's an Excel table. Let's take a look at this one first, so you have a better idea what I'm talking about. And let's see here. Okay, those are the types of glass that they have. They call it SK, PK, PSK, and so on, right? And we see in each type of glass they have subtypes. F it has to do with the chemical composition of the glass. Okay, they have all sorts of glass. Most of those glasses have a refractive index that we see in 1.5, very close to 1.5. Okay, here is another formula for the refractive index for the dispersion. Okay, it's a more complicated formula, but a first order approximation is that one that I showed to you, inverse of the wavelengths. Temperature, color code, okay, relative partial dispersion. So you see that other characteristics of the glass, they have not just refractive index characteristics, but others too. Okay, we are interested most in refractive index. There's a dispersion, here's the dispersion formula that I mentioned to you. Okay, we are not interested in this one, we're just interested in the behavior of the wavelengths with behavior of the refractive index with the wavelengths. Okay, and refractive index, here you go. Refractive index for this glass right here. Notice the refractive index that I told you is very close to 1.5. See, 200 to 2,325 nanometers, which is in the infrared, by the way. The refractive index is 1.46180. See how small the difference is? If you go all the way to 1,060 nanometers, which is still in the infrared, the refractive index increases. Okay, lower wavelengths. Okay, and do you see that they have okay, internal transmittance. Okay, we want to know about the refractive index again. And here are the other wavelengths for that specific glass. Okay, we're going closer and closer to blue. Okay, now here is already in the ultraviolet. This region here is already in the ultraviolet. Notice that the refractive index decreases with the wavelengths. So let's see. The refractive index is increasing as the wavelengths decreases. It's an inverse relationship. Here's an actual real world glass that we have out there. Most optical materials behave like that. And then there's a specific materials that don't behave this way, but they're exception. Here's the data sheet for this other glass, NFK5. Okay, remember we're just concentrating on the refractive index, right? And then, you know, all this table, remember, You know, at the time, I got them in a binder with several pages in there. Nowadays, we put everything in a single PDF document, right? Here you go, glass K7. Remember, glass has a refractive index very close to 1.5. Rarely you're going to find a glass with refractive index greater than 2, okay? Unless it's an exotic material like diamond, 2 point whatever. Well, let's see if I can find a glass with, no, that's a wavelength. That's not refractive index, right? Oops, what did I sign here? Oh, here. Okay, let's see. 2.3 as a chemical property, has nothing to do with refractive index. That's the density, has nothing to do with refractive index, right? But take a look, and they have a table too that lists, you know, everything 1.5. Oh, see, now the refractive index is increasing from 1.46 to 1.7. See that? Those are exotic materials, exotic glasses. Let's go to the bottom, 1.6, 1.7. Let's see at the very end here. Yeah, 1.8. Apparently, they don't have glasses with more than 1.8 in refractive index. SF is another type of glass. At that time, I bought a bunch of different glasses, rods, because I want to make optical fiber out of them. When I was working at NASA, I did it. And I bought those, you know, optical rods to make an optical fiber, but then at the end, I didn't use it. They have a graph that I'm trying to find out where their graph is. It's not here. Yeah, it's not here, definitely. Let's see, optical glass, inquiry glass collection data sheet overview. There's an Excel table. I don't want the Excel table. Optical glass, Zmax, high modulation glass data sheet, optical materials for precision molding, test glass. Let's take a look at this Excel data sheet. Okay. All the graphs, most likely all the glasses, all the refractive index of all the glasses are listed in this Excel data sheet. Let's see if that's what it is. Datable, no, it's not what it is. Unfortunately, that data table. Okay, oh yeah, here you go. Yeah, they have it. Okay, each of the values that you see here is a refractive index at a given wavelengths. And then they have the dispersion formula, okay, the constants of the dispersion formula, and that's all we're interested. Unfortunately, they do not have as extensive table as the one that you saw in the PDF document. But here is the wavelength, is the refractive index at a given wavelengths, 2 different wavelengths. Okay. BK7 and so on. Let's see if they have 2.0 there. I don't think they have 2.0 there. See the number? Oh, yeah, they do have it. See here? This glass, it has a refractive index that's very high, 2.005. A special glass, exotic glass. Okay, 2.005 is rather high. Okay, so we are interested in this part here. Unfortunately, they don't have the other wavelengths here, unfortunately. Even though they don't have the other wavelengths, they do have the constants of the dispersion formula that you can calculate to derive, to obtain the refractive index. 957 already. So that's nice to have. It's nice to locate after so many years. You know, I finally look at the shot website. Overview Zmax format, inquiry glass overview, high homogeneity glass data sheet, and so on. Press, yeah. So the interesting thing is this data sheet here and this other one here. This is just an overview. So let's take attendance. 9:57 right now. Any questions? let's move it. Go. Chat, no messages for me, and I got this one here. Lecture attendance 8:15, 5:15. Randy Bautista, are you there? Hello, Randy. Yes, good. Thank you, Randy. Next is Vanessa Bonilla. Thank you, Vanessa. Ashley Diaz. I don't see Ashley here in my list. Natalie Espinosa. Thank you, Natalie. Jeanette Garcia. Hi, Jeanette, are you there? Okay, thank you. Noor Hassan. I don't see Noor here. Blanca Hernandez. Thank you, Blanca. Kelly Hernandez. Next is Joshua Jimenez. I don't see Joshua here. Next is going to be Alondra. Alondra is always the first one, right, to arrive here. Are you there, Alondra? I see her in the list. Okay, I'm going to put a star in Alondra's attendance here. Kennedy.
I'm here.
Thank you. Thank you. Daisy Mariscal. Daisy. Yeah, good. Thank you, Daisy. Elika is coming. Yesenia Montes Rodriguez. What happened to Yesenia? Next is Ryan Ong. I don't see all Ryan's in there. Thank you, Ryan. Daisy Mariscal here. Good. Arthur Pacheco. Arthur Pacheco is here. Okay. Thank you, Arthur. Labelud. Next is Donia.
Here.
Thank you, Donia. Elika. Elika just joined us.
Here.
Okay, thank you. Brianna Valencia. I don't see Brianna in my list. And Justena Youssef. Okay, and let's see how many students are here. 10 o'clock right now. 14, 15, let's see. Okay, so it's 10 o'clock right now. Let's take a break. Break from 10 a.m. to 10:15 a.m. And I'll see you in 15 minutes. Okay, so I'm going to give you a reference for that website, short glass website reference. This one here. With the data sheet. So you have a feeling how the refractive index of glasses work. And there was that other one too, right? Oh yeah, that's the one. The one that you should be concentrating on is this optical glass collection data sheet and the Excel table here. Okay. If you're going to concentrate on the following links: optical glass collection data sheet and the optical glass overview Excel table. Don't forget that the data sheet is has far more information than this overview here in the Excel table. Oh, what's going on here? I created a link, optical glass collection data sheets. Optical glass overview Excel table. Like that. And that's this section on dispersion. Okay. Applications of dispersion. One important application of dispersion. I already wrote that down, right? Yeah, already wrote that down. With a spectroscope. That's one important application of dispersion. Here, the droplets, whenever it's raining, the droplets disperse the light. That's why you end up seeing the rainbow. The geometry of the situation is such that we end up seeing this rainbow because of, of dispersion and because the droplets, water droplets behave like a little sphere. Lenses. Now we're going to go into lenses. Okay. And what you're going to see here in lenses is very similar to what we saw in mirrors. Next section, lenses. 26.6. This section is very similar to the one we covered in spherical mirrors. Spherical mirrors, even the equations are similar. The device is different. Light behaves differently, right? Reflection versus refraction. But the final formulas are exactly the same. Not very similar, but exactly the same. And it's not any type of lenses, okay? We're talking about thin lenses here. If the lens is thicker, then the formulation is more complicated. So this is what you're dealing here with is with an approximation. In other words, what we are dealing with here is an approximation. The final formulas are exactly the same. Okay, so here you go. Here we have a very simple way of visualizing what a lens does to the path of the light. Okay, consider, a very simple lens that's a triangular shape, and they're both triangular shape, and we put them together like a prism, right? One prism upright and another prism upside down. So how light behaves? In this configuration here, light tends to be focused along this line. They're not focused exactly at the same point. Okay, exactly because of the geometry of my lens. However, if I create something more complicated than that, okay, not a lens with straight surfaces, but a lens that has a spherical section on both sides, okay? If we do that, this lens is going to be able to concentrate all the light in a single point. Light, for instance, from an object that's very far away. That's what those parallel rays is all about, okay? Let's write it down, okay? Parallel rays parallel light rays are rays that, very important, that come from an object that is very far away from the lens or mirror, okay? The sun, for instance, the light rays of the sun, for instance, is said to be parallel to the principal axis of your lens or mirror. Okay, the light rays of the stars too, the light rays of the stars as well, and the moon, etc., Okay. How do we judge whether an object is very far away from the lens? Well, the distance, P, right? P that we know, D sub O, right? D sub O must be much greater than the diameter of the device, whether it's a lens or mirror. Must be great, must be, it should be lowercase d, I want here. Diameter of device, lens or mirror. Okay. And a very good approximation for that, for much greater than the diameter, should be, 10 times greater, 10 times greater than the diameter of the lens. The lens is slash mirror. That's how we decide whether the object is far away. At this point here, we can say that the light from the object are coming very close to the light rays of the object are becoming very close to the parallel direction of the lens or the mirror. Yeah, would be let's not the diameter of the device. There's a better way of let me correct that, okay? Much greater than the focal distance, okay, of the lens or mirror. Focal distance would be a better way to mensurate that. Or DO must be greater than 10 times the focal distance, 10f. I'm going to put 10 lowercase f. That would be better. That would be a better definition. It makes a huge difference. Okay? Focal distance of the device. Okay? Then, if this condition satisfied, we can say that the light rays are traveling almost parallel to the axis. Okay, if this condition is satisfied, we can state that the light rays are almost parallel to the principal axis of the optical device. Okay, and that's what you see right here. Okay, this object is 10 times, no, it's a distance 10 times greater than the focal length or the focal distance of your lens. Okay, the procedure to form the image with a lens is very similar to that of the mirror, the one that we did for the mirror. Let me get this 39 right in here. Focal distance. Let's see if I have some. Yeah, that's for the mirror. Okay, here you go. Starts here. I'm gonna copy everything and paste there in your. Okay, copy and paste. Okay, here you go. What we have here is a spherical lens. How do we make a spherical lens? Well, just like we did a spherical mirror, we take a piece of glass in which at least one of the surfaces is a spherical, is a section of a sphere. We can have, like in this case here, what we have is a convex lens. Okay, convex, because we have a bulge here. Plain convex lens. The surface of the lens has a given radius of curvature. This other surface here has a radius of curvature that's infinite. Okay, planar. We have different types of lenses. Let's write that down. We have different types of lenses. We have one, planar convex lenses, planar concave lens. We have biconvex, right? Biconvex lenses. We have biconcave lenses and everything else in between, and everything else in between, okay? And everything else in between. What you saw there was a planar convex lens. Let's make a little of a table here. Differences, important differences between mirrors and lenses. Okay, insert table. Okay, mirror, lens, concave, concave mirror, concentrate light, concave lens. And here we have concave and convex. Diverge light rays, okay? No, concentrate parallel light rays. Parallel, let's put it this way. Parallel, the light ray must be parallel. Diverge, parallel light rays. And important difference is that the situation is switched for lenses. Okay. For the case of the lens, I'm assuming that it's a planar convex lens. Okay. Let's take a look here. There's a very good way here to visualize what a lens does, okay? See that this lens here, because it doesn't have a spherical surface, it has multiple foci, right? In order to bring all those foci together, we must come up with a spherical surface to focus the light in a single point. Okay, and then we have, here's the divergent lens, right? Here's a biconcave lens. Here is a biconvex lens. This definitely diverge the light rays. This definitely converge the light rays. But then there are, a combination. Oh, here you go, double convex, planar convex. This is a convex meniscus. Note that both surfaces are spherical, but that they have different radii of curvature. This surface has a radius of curvature that is smaller than this surface. The shallower the surface, the larger the radius of curvature. Okay, so let's write it down here. The shallower the surface, comma, the larger the radius of curvature of the surface. Okay, the shallower, the deeper, the deeper the surface, the smaller is of the curvature of the surface. And that you can, you can convince yourself by drawing different circles, right? The larger this radius of curvature here, the shallower the surface is going to be, right? And remember that what I have here is actually it's a circle that I drew. That's why let's see if I can. Yeah, here you go. I'm uncovering what's behind, okay? I'm uncovering what's behind. If I make a larger circle here with the center shifted, you're going to see that the surface is going to be shallower, right? That applies both to lenses and mirrors. Okay, so here you go. Planar convex lens. We go ahead and put the principal axis of the lens, and we start playing with light rays. Here you go. If we have a light ray coming parallel to the principal axis of the lens, it's going to be refracted within the lens. Because the surface to the left is planar, light is not going to be refracted at all, because the incidence is normal incidence. However, when it reaches the curved surface, see, we have here the line that's tangent to that point. I'm going to draw the normal to that surface. The normal to that surface. And what this light is going to do? This light is going to diverge from the normal. Okay? Here you go. Here is the direction of the original path ray of the path of the ray, right? We call it the goes through light ray. We use that as a reference to draw my refracted ray. Here you go. That's where my refracted ray is directed to. Is moving away from the normal. Okay? That's how light behaves in this planar convex lens. Okay? This point that the light is converging towards is called the focal point. And the distance from here to here is the focal length. Okay? If we do to several light rays, we find out that all parallel light rays are going to converge at that point. We're not forming the image yet. We're just playing how the light ray behaves with a lens, okay? The symbol of a lens is this one that you see right in here. It's an arrow with two, it's a line with two arrows. That's the symbol of a convergent lens. Okay, the symbol of divergent lens. Let's see if I have that for you, so you can have that as a reference. Yeah, that's the symbol of a divergent lens. I'm gonna just put the arrow upside down, right? The tips of the arrow upside down. I'm gonna erase everything else. Like that. Here you go. That's the symbol of a divergent lens. Convergent lens symbol. Okay. Convergent lens symbol. Divergent lens symbol. Going back to my convergent lens symbol, we're going to concentrate on the convergent lens. Okay, go. If I want to draw the image, we have to set up the main axis of the lens, just like we did for the mirror. Right? We have to put the focal point of the lens. By the way, the focal point of the lens is going to be opposite to that of the mirror, right? It's going to be behind the lens. For the case of the mirror, the focal point was in front of the mirror, right? For the case of the lens, the focal point is behind the mirror. So those are important differences, right? Let's see if I can document. Convex, concentrate, let's say focal point, front, in front of the mirror, behind the lens, oh. But behind with respect to the object, right? With respect to the object. If the object is in front of the lens, then the focal point is going to be behind the lens. If the object is in front of the mirror, the focal point is going to be in front of the mirror. Like that, focal point. Similarities and differences between mirrors and lenses. Let's not forget we're talking about the spherical lenses here. Spherical lenses. The spherical thin lenses. By spherical thin lens, you know, a thin lens means what? The thickness of the lens is much smaller than the diameter of the lens. Thin lens. Definition. Thickness of the lens is much smaller than the diameter of the lens. Okay? That's how the definition of thin is. Going back to my drawing here, focal point there, right? And then we have this other focal point that's in front of it. It's going to be useful when we draw the images. We call that F prime. We put an object in front of the lens, And we are going to draw the image using exactly the same procedure that we saw. First, light rays parallel to the main axis. Light rays parallel to the main axis are refracted towards the focal point of the lens. Remember? The mirror. Light rays parallel to the main axis of the mirror are reflected towards the focal point of the mirror. Light rays that pass in front of, that pass through the point F prime are refracted parallel to the axis of the lens. Okay, and that's the goes through light ray again. And then we have this other, I don't know, let's get that here. Right from here. Next, I don't want to put the goes through light ray there. Looks nicer now, right? Yeah. And we have this third light ray that passed through the center of the lens. The light ray that passed through the center of the lens travels unrefracted. Okay, with the same angle. The intersection of all those light rays refers to the intersection, refers to the point of the tip of the object is formed. Okay, look at the image. Image is real and inverted. Image is real and inverted. So the important difference here is this one, right? Everything else is the same, almost the same. That's the distance of the image, distance of the object, distance of the image. That's the focal distance, right? And now, what if the object here are different examples, right? How you can form the image. What if the object is at the focal point, at the F prime point, right? Which is the same distance as the focal point. Okay. The image that's formed is improper because the image is formed at a very large distance. So let's summarize. Let's document that what I said first. Okay. Object placed in front of the lens at a position greater than F. Okay. One light ray parallel to the axis is focused towards the focal point. Okay. Light ray passing through the F prime point at distance F in front of the lens is refracted. Let's see. Is refracted. Here you go. Let's put refracted here. Put the focal point. This one is going to be refracted parallel to the axis, to the main axis or principal axis of the lens. 3 light ray that passes through the center of the lens follow its path unrefracted. the intersection of these three light rays, defines the tip of the image of the object. Okay, light ray, let's see. Light ray coming from the tip of the object and parallel, right? Jet. And here you go. Let's do this differently. Here you go. Parallel to the axis is refracted like this way. Light ray coming from the tip and passing through F prime. And this is F from the. This is F from the front of the lens. It's refracted parallel to the principal axis of the lens. Light ray coming from the tip of the object and passing through the center of the lens, follow its path unrefracted. They don't, and then we have this other one. The intersection of these three light rays defines the tip of the image of the object. Okay. Let's take a look at the simulations for lenses here in the internet. There's a bunch of simulations. Simulation of lenses. Concave, maybe this one. Let's see if this one is good. Okay, here you go. Spherical lens, right? Spherical. Let's see if I can move my focus. Yeah, I can move my focus. See that? I can move my focus. This focus is 2 units. The distance of the object is 8 units. Let's see if I place it here. Something like that. Note, see that those light rays, they are almost parallel to each other, right? Because the light rays are almost parallel to each other. When the focal point is like 1 unit and the object is 10 times the distance from the lens, you know, the light rays are almost parallel to each other. Those 2 light rays are almost parallel to each other. And the image is formed very close by the focal point, right? So let's keep the focal point here. Here you go. But here what we have, light rays parallel to the axis, light ray passing through the focal point that's in front of the lens, and light ray that pass through the center of the lens, undeflected, refracted towards the focal point, refracted parallel to the axis, and unrefracted. Okay. And now you can play with this arrow, you know, further away, okay, closer, okay. Now look what happens whenever I put the object exactly at the focal distance from the lens. That no image is formed. We call it an improper image. Improper image. Let's see here. Object placed a distance f in front of the lens. Okay. Image formed is improper. Here in this case, image is real and inverted. And by the way, object and image are real. Why am I doing that? I'm doing that because we may have virtual objects, okay, but we are not going to cover that in this course. Object and image are real. Let's see. Object real. Image is real and inverted. Like that. Is improper. Object image form is improper. Now we are going to, again, no, just playing here with the object in the focal point, right? Here you go. Parallel, refracted towards the focal point. Light rays that passes through the center of the object ends up being parallel to this light ray, and the image, is improper. Any light ray that leaves the tip and passes through the focal point f prime, is never gonna cross the lens. Okay. Now, what about the next one? Here you go. What about if we come up with the object closer, even closer to the lens? I'm going to make a better. Refraction. This line here is too thick for me. Size and position. No, it doesn't work. Maybe here, reflection glow, 3D format, fill line. Must be this one. Okay, now let's make it smaller. Better now, right? So here you go. Look here, by 3 light rays. I will break it down in several light rays, little by. No, let's see. I'll do that here. Now let's see. Right? Light ray parallel to the axis is focused towards the focal point. Okay. Another one here. Light ray that goes through the center of the lens, follow unrefracted. Notice that those 2 light rays are diverging from each other. What does it mean? It means that there will be no image forming on the right side of the lens. And then we have one more light ray that passes through the focal point in front of the lens. Is refracted parallel to the axis, to the principal axis. Notice that it doesn't matter if the lens is shorter than is smaller than the point here. Okay, you still can do that. It is as though the lens is extending infinitely up and down. Okay, so I'm gonna put that here like that. Right? So here you go. Take it out. Put like that. So those are all my 3 light rays. What else do I have to do? Since the image is not forming on the right side of the lens, it must be forming on the left side of the lens. And how do you form this image? Okay, we form this image by stretching all those lines to the left. If I did everything right, all those 2 lines are going to intercept at the same point. Right in here, okay? And now we end up with an image that is virtual because it's in front of the lens and larger. Okay, and by the way, that's exactly how a magnifying glass works. That's exactly how a magnifying glass works. You put an object in front of behind your lens, right? And then you're going to see a larger image. Okay, so what I'm going to do here, object image is real, inverted, and I have to write something else here, and smaller, by the way, okay? That's for the previous one. This one is going to be larger, okay? Let's take a look at the other one. Okay, this object here is going to be smaller. It doesn't look like, but it's going to be smaller, okay? Let's see here. No, wait a minute. Well, it all depends. There's a little bit more to that, okay? It all depends where the object is. So let's take a look. Yeah. If the object is actually, if the object is between the focal point, let's see, is between twice the focal point and the focal point, is going to be larger, okay? So past the focal point, let's see, objects placed in front of the lens at a position greater than, let's put 2f, like that, greater than 2f. You can see exactly at 2f, twice the distance, the focal point, the focal distance, the image of the object is exactly the same size. If we pass it further, you're going to see this is smaller, okay? When the object is between, I gotta put another one, okay? So let's put that. When the object is between, object placed and smaller. Now, object placed at a position in front of the lens at a position between f and 2f. Okay, it's the same procedure, but the difference here, the image is still going to be inverted, but the image is going to be larger. Object is real, image is going to be larger. Okay. Object placed at distance f in front of the lens, image form is improper, and then object placed at distance less than f in front of the lens. What happens? That's what we're dealing right now. Right? Let's go to the other. Right here. There you go. Image formed in front of the lens is vertical and larger than object. Upright and larger than object. And then you, in order to find that out, you do, all that stuff that I mentioned to you. Those are the 1, 2, 3, 4 conditions, right? Situations that you're going to find. I'm gonna put no. I just continue numbering. Not what I want. Set numbering value here. Number 2. Takes so. Oh my goodness. Oh, there's a bug in the software. I can't stand it. Okay, so here you go. Light and maybe I got my computer got a, yeah, it's returning. I'm not gonna struggle with that. Okay, so 1, 2, 3, 4, right? I even tried to change the number, set numbering value, but it's not doing it. 2, 3, 4. Yeah. Huh. Interesting. It's doing it, but it's changing the position. Oh no. Oh gosh. Not responding. I hate when that happens. Okay. Now let's see if I can change the position. I'm gonna put a 3 here. Gonna take a long time. Oh no, it didn't take a long time. That's good. I'm gonna put 2 here. That numbering value, 1, 2. Oh yeah, I don't know why he's doing that. Huh. Yeah, it's getting worse than I thought. Okay. Let's go back to what we have here. Sorry, folks, I cannot do better than that. Software is not cooperating. We're going to start breaking down this document into multiple documents, okay? But let's go back to our simulation, right? Where's our object? Okay, go. So we started far away from the focal point. Image is smaller, brought it closer when the position of the object is twice the focal distance of the lens. The size of the image is the same. Magnification is 1. When we start approaching towards the focus of the object, the image becomes larger and larger until it becomes improper. The image is so large that those 2 light rays do not intersect each other. Okay? Past this, that's how the story goes. Past the focal point, the image becomes improper and it's larger than the size of the object. I'm going to decrease it. Here you go. It's larger than the object, even smaller. Okay. Doesn't matter where the object is. Okay. Doesn't matter where the object is. Don't forget, we're talking about a scene lens. It is as though we do not have a surface here. We do not have a surface there. Okay. So that's how this thing behaves. Okay. It has a progression, right? And what else do we have to know? Okay, the formula of the scene lens. Formula of the scene lens is exactly the same, as that for the mirror. Let's go back to our formulas that we formulated before. Go, that's this one here. Okay, and we also have the magnification. I'm gonna put them side by side so I can copy everything. Okay. How do you obtain these formulas? Using similar triangles. Using similar triangles, which basically is geometry, right? That's why it's called geometrical optics. Using geometry, we have distance of the object, and then the magnification is the same. Let's take a look here. Not this one, is this one here. Formation image by lengths, okay. See, passing through. He call it F and F. No, I prefer to call it F prime. And the same thing applies to the divergent lenses. 1110, 1109 right now. Okay. And let's take a look at the simulation for the diverging lens. Let's see if I can get it here to change it. How do I change that? Maybe here? No. Convex lens. Yeah, okay. Description. Well, let's have our break, right? And then I'll get the. Sometimes you have to. Yeah, it's not cooperating. Physics interactive. Let's have our break. Right now it's 11:10, and then we go for the divergent lens. Break between 11:10 and 11:10 a.m. and 11:25 a.m. Okay, so any questions? So I see you in 15 minutes. Okay, we are back here, 11:25, and what else we have to cover? Let's take a look. Next. Right, so we covered, we have to take, we have to look at convex lenses, right? So let's see. How can we change to convex? Must be, okay, that's how we do it. We have to play with the focus of the lens, okay? Notice that that's here is positive focus, right? See that positive, negative, okay? So this the biconvex lens has a positive focus, but a concave lens has a negative focus. Okay, see the difference between them? So let's take a look. That's going to be shallower. That's convergent lens, right? Convergent lens. Now we're going to do divergent lens. Divergent lens is easier than convergent lens, okay? It's easier because it has less conditions. Divergent lens. Divergent lens, okay? F is less than 0. F is less than 0, okay? In front of the lens. Focal point is in front, or focal point is in front of the lens. Okay. This is simpler. Image formation is simpler. Image formation is simpler because we have just simpler because we have just a single condition, a single result. Let's go here. Okay. So let's take a look here. Here's the image. Here's the image. Here you go. Light rays parallel to the primary axis diverge towards the focus. Okay. In the other one, light rays parallel to the axis converge towards the focus. Here you go. Converge towards the focus, right? Now it diverge. Not toward the focus, but away from the focus. Diverge away from the focus. Let's write it down. Object placed in front of the lens at a position greater, placed in front of the lens. Light ray coming from the tip of the object. And parallel to the axis, it is refracted away from the focal point. Okay. Passing, well, let's take a look at the other one. Right. Now, light ray, going towards towards the F prime, going towards the F prime is refracted parallel to the axis, right? Let's compare that to the previous one. Light ray, passing through F prime is refracted parallel. So it's similar, right? Let's change it again. Oh. Right? So this light ray is aiming at the F prime point. Okay. Light ray aiming towards F prime. Refract a distance F from the back of the lens. From the back of the lens is refracted parallel to the principal axis of the lens. Parallel to the principal axis of the lens, and then you extend it to the left, right? So now I already have 2 points. I have already the intersection of 2 light rays. Okay. And then we have this light ray that passes through the center of the lens that goes undeflected, right? Passing through the center of the lens, follow its path. Let's see. Through the center of the lens, follow its path unrefracted. Let's see if he likes it now. The intersection of these 3 light rays define the tip of the image of the object. Object is real. Image is virtual. Upright. And larger. Upright. Object is real. Let's put it this way. It's real. Image is virtual. Okay. Now let's play with this guy here and see if we get anything else that's different than what I told you. Okay, whether I put my object. See, my object is always going to, my image is always going to be virtual, and it's always going to be upright, and is always going to be equal or less than that of the object, okay? So that it doesn't matter where the object is placed. In this case, okay, the final result applies to any position of the object. So that's why I say it's simpler. Okay, so here you go. Here's the illustration, right? Here's the mirror, and yeah, that's there you go. That's what we have for this chapter, for this section. To 26.7 as well. Scene length. Oh yeah, what about the scene length and magnification? Same thing, right? Scene length equation is the same formula. Okay, and the magnification. Okay, see that the equation is the same. Same equation. There you go. For both lenses is the same. The difference is just the sign. Focal distance for positive lens is greater than 0. Focal distance of negative lens or diverging lens is less than 0. Okay, so those equations here apply both for lenses and mirrors. And let's see. So practicing how you're going to do the, practicing with those light rays the way you see here. Okay, and then we have lens combination. I'm not gonna do lens combination. Ideally, we should be doing, but we're running out of time. Okay, let's see. we have some of the section anatomy. Okay, how the human eye works. We're going to cover that. The human eye is rather simple. The human eye is just like a converging lens. It's a positive lens that behaves like a positive lens. Okay, and that's what we have right here. We have, see, light ray parallel to the main axis, principal axis of the lens of the eye, passes through the focal point and is imaged at the retina. And the brain processes this image. You know, the image ends up being upside down, but the computing power of the brain is large enough to make to process the image and make it upright. Okay, so there is a processing that's done by the brain. Close objects is like that. So it's no different from, and the nice thing about the lens is that it has a variable focal point. Okay, let's about the eye, right? About the eye. Let's write here 26.10. Skip 26.9. Skip 26.9. The human eye, 26.10, the human eye. Okay. The human eye behaves just like a convergent lens. Most of its refraction is provided by the lens in the eye. Okay, but then there is some refraction also. There's some contributions to the refraction by the other parts of the eye. The cornea, for instance, contributes to the refraction, and other. Okay, and the lens, the human lens has this capability of changing its focal length. Okay, we have muscles in the eyes that change the curvature of the lens. Do you see here? Here we have one curvature. He calls it the relaxed lens. That whenever you are looking at objects distant, that are distant. But as the object gets closer and closer, then the muscles apply some force on the lens, and the lens becomes with a smaller curvature. Okay, the focal distance of the lens changes because we have a different radius of curvature in both sides of the lens, of the human lens. Okay, now what else do we have to know? Okay, so here we go. Now we have the situation. We have near sight eye and far sight eye. We have those two conditions of the human, two adverse conditions of the human eye, adverse conditions of the human eye. Nearsighted eye and far-sighted eye. Okay. In a nearsighted eye, the focal point, the focal distance of the lens is shorter, then let's see. No, it's not a good way of putting it, you know. And they didn't illustrate it properly either. Okay. Okay. In the nearsighted eye, the image of the object is formed before the retina. Okay, before the retina. This is because has nothing to do with the lens. This is because the eyeball becomes stretched longer or longer. Okay. That's the reason we end up nearsighted. So let's say if this is the normal eye, right? A nearsighted eye is something like that. I'm exaggerating, of course. And because of that, the image is formed before the retina. And the eye cannot focus properly the image. Here's the normal eye, nearsighted eye. Okay. Normal eye. Nearsighted eye. So you can see only things that are close. That's why you are called nearsighted. Longer. Or longer. And you can focus only on the objects that are closer. Objects that are further away are focused before the retina. Farsighted eyes, exactly the opposite. Okay. In a far-sighted eye, the image of the object is formed after the retina. This is because the eyeball becomes shorter. Okay. And can focus only on objects that are distant. Can focus only on the objects that are distant. Okay. So here we go. Normal eye, far-sighted eye. Far-sighted eye, far-sighted eye. I'm gonna copy this guy again and I'm gonna put it here. It's gonna be like that. Exactly the opposite. Okay. So we can come up with a drawing, right? Here's my lens. Here you go. I'm gonna use that as the model of my model of the lens. Here you go, model of the lens. Everything else being the same, the image is gonna form exactly at the same place, right? So here you go. Image forms exactly, let's see here. And because the focal distance of the lens, because the focal distance of the lens did not change. Okay, now the image is being formed before the retina. And here the image is being formed after the retina. Let's get here you go one. Right in here. Right in there. Model of the eye. Because well, so for far-sighted eyes, the image gets closer and closer to the objects that are further and further away. They get closer and closer to the retina, right? That's why they're called far-sighted. Gets closer and closer to the retina. I'm putting that in the wrong place. Let me put in the right place. This one here. Huh. Right here. Okay. This one goes here. Like that. So the further away the object is, the closer it gets to the retina, right? Sorry, the closer away the object is, the closer it gets to the retina. That's the right drawing, right? The closer it gets to the eye, the further away the object is formed. The image is formed. Okay, so let's write it down. Okay. Recall from the behavior of a positive lens. 1. The further an object is from the lens, the closer the image, the position of the image gets closer and closer to the position of the image, gets closer and closer to the focal point, right? That's what those results tell us, right? Where is the... Oh, here you go, this one. Going back to our positive lens. You go, positive lens, right? The further the object is, the closer the image gets to the focal point. Okay. The further the object is, an object becomes from the lens, the closer its image gets to the focal point, like that. The closer an object, now I got just a copy here, right? The closer an object comes to the lens, the further its image gets is formed from the focal point. Is formed from the focal point better. So here is here's the far-sighted individual. Far-sighted individuals, do better with this type of images. Far-sighted individuals can see this is better for farsighted individuals. This is better for farsighted individuals. This is better for nearsighted individuals. This is better for nearsighted individuals. That's what you have to know. So everything that we learn about optics fits into the human eye. Okay, and how do you fix that? How do you fix that? Okay, going back to our drawing here. Okay, in order to fix this condition, in order to fix this condition, we have to combine the lens with another lens that will place the image further away from the eye. And which type of lens do you have to use? Let's see. Is it the one? Oh, that's not the one. Mixing up. This one here. Must be this one here. Yeah. Okay, now we have to use a diverging lens that will correct for this condition. Oops. Oh, there's more. Okay, by putting a divergent lens here, the image will be formed further away because this lens diverges the light. Okay? Nearsighted eye corrected with negative lens. That's the case of my lens that I have right here. Okay? If I look through my lens, I can see that the objects are smaller, just like we have predicted. But on the top of that, it also places the image of the lens further away. So you have to use the proper lens to correct for that. And what about this one here? It's all the way around. It's all the way around. In order to correct for a farsighted eye, the individual. Oh, I don't. Yeah, I didn't put my lens here in that figure. Let's put it now. Okay. Right here. For a farsighted individual, we have to use a positive lens to correct the position of the image. Okay, those two important pieces. So here what we have a combination of lenses, right? One lens with another. We're doing that just in a qualitative fashion to correct for these conditions. To correct for these conditions. A nearsighted eye must wear a negative lens. And one. And two, a far-sighted eye must wear a positive lens. That's what we have, and That's what I have for this chapter. And 1156. I'm not gonna cover that. Okay, we're gonna stop here in this chapter. And magnification, magnifying glass. We're not gonna do the rest. So when I stop writing here, just the human eye, and I'm going to list the chapters of this, the sections of this chapter. Sections of this chapter. Unfortunately, we don't have time to do everything that I would like to do in this chapter because there's so many neat things, especially the telescope, combination of lenses, telescope, compound microscope, and so on. The least that I can do is the human eye, but let's write it down. 36.1, 26.2, 26.3, 26.4, 26.5, which is dispersion, 26.6, that's lenses, 26.7, lots of sections. See that? The thin lens equation, we did the thin lens equation. Lenses combination we didn't do, then we skipped to 26.10. And that's where we stopped. Now, if you had more time, we could do it, but I want to get into the other chapters here, especially relativity. Okay, any questions? Let's see if there's any messages here. Okay, so don't forget the exam is on Wednesday, right? And I have office hours right now. And if you need anything, just hang around and I will see you on Wednesday. Thank you for coming.
Thank you, Professor. Have a good day.